So I know about half of you, or at least I know your names and Zoom profiles. So welcome. It's nice to meet you in person. The other half of you, welcome. I'm Dr. Beiersdorf. Hopefully, while you were waiting, I know we weren't here very long, but you saw this slide. If you go to the App Store or the Google Play Store, there's an app called Zapper that we're going to be using, probably starting next week. But if you would download that, that would be helpful. Is there anybody here who is not enrolled right now? Who's looking for an ad code? Okay. So I don't have ad codes to give, and you can't actually stay because of capacity limits. But I can tell you to go to the physics department website and request an ad code there. And I can also tell you before you leave that I am recording this. So if you aren't able to get in until next week or something, all of the lectures will be recorded. Okay, thanks. I'm Dr. Beiersdorf. Easiest way to contact me is either via email or through Canvas. I did put my telephone number. Oh, I don't. My telephone number is in the syllabus. It's probably not very helpful if you call it. It's just a landline in my office. But I put it there because sometimes people need like a reference on a job application or something like that and need telephone numbers. So yeah, email is the best way to contact me. But I'm not the only member of our instructional team. Did Sia make it yet? She's running late, but we have Sadhna and Joy, who are learning assistants. So I'm really excited to have them in the class. Their job is to help facilitate the classroom learning. So they will be circulating around when we're doing group activities, and they're there to help sort of be a conduit between myself and you so that you have someone you can talk to, ask questions to. There are students who have taken this class before, but they're not here to be tutors or to be subject experts. They're here to facilitate the learning and help you ask the right questions and be thinking about things the right way. And so their contact information is up here as well. Pretty much everything you're going to need for the course is on Canvas. So our names and contact information is on Canvas. All the class notes, so the PDFs of the files that I'll present, office hour info, everything like that, will be on Canvas, as well as the homeworks that you'll be doing. So make sure to log in there if you haven't already. I sent out an announcement, and it looks like most of you have already done that first assignment, which is a College of Science bookkeeping thing where you have to download a form, read through the Canvas, through the San Jose State COVID plan, and then sign the form saying that you've read it and upload it. Okay, so that's obviously nothing to do with physics, but it's something that the college is making all of the classes do as their first assignment. That is due on Tuesday. Okay, so you have to get that completed. So hopefully once you read through it, you can just sign that form for every class. Maybe just keep a hard copy you can photograph and then upload to every class that asks for it. I mentioned on Canvas, that's where you can find the homeworks. The way this class is structured is slow and steady. So pretty much every class, you're going to have an assigned reading to do beforehand, and then a very short quiz about the reading, and then a homework assignment like working out problems to do before the next class. So you should structure your time so that you have an hour or two before every class to go through and do those activities. There are no midterms or final exam, so there's no need to be like cramming for anything a month from now, but it's really important that you keep up with things as we go, because all of those assignments as we go through, those will be your whole grade, since there is no midterm, there is no final exam. So you don't want to put that off until mid-October and then say, how can I make up the work, because it'll be too late. Okay, so stay on top of things. That's my advice for structuring your time to succeed in this class. When you work out the problems, you'll be given end of chapter problems to work out in the textbook before every class. So work those out on a piece of paper, bring them to class, You're not going to be turning them in, but we will occasionally do group work based on them. So you're expected to have attempted the problem so you can talk to your group about what you did, how you did it. And those homeworks will form the basis for the quizzes, which is where you'll actually score points. Okay, so roughly once a week, we'll have an in-class quiz, about 20 minutes long. It'll be on the topic of whatever chapter we just covered. It'll be very closely tied to the homework on that chapter. So while you're not turning in the homework, if you can do the homework, you're going to ace the quizzes. Okay, if you're stuck on the homework, ask me for help. Okay, there's no reason to get lost. So roughly one per week, and they will form the bulk of your grade. 70% of your grade will be these in-class quizzes. The remaining 30% is going to be split between the short reading quizzes that you do and then the lab. So you'll get a score from your lab instructor. That'll be 15% of your grade. The reading quizzes are meant to be super easy. There was only 2 questions. They're multiple choice. If you do the reading, you should fly right through it. And you get 15% of your course grade just for doing that. It's just a little incentive to make sure you're keeping up. I really want you to keep up with the readings because I want to use class time to focus on stuff that we can't do outside of class. After a year being on Zoom, I'm going to try to avoid just lecturing for 75 minutes. We're going to try to do group activities, demonstrations, things that are supplemental to what's in the textbook. I'm not just going to go through the entire chapter. So there are things that I don't want to fall through the cracks. You need to read the textbook. Okay, so the quizzes are 70% of your grade. There will be roughly 1 per week. At the end of the semester, I said we won't have a final exam, but what we will do is we will meet and you will be allowed to retake your 3 lowest quizzes to replace the scores. Okay, so essentially you get your 3 lowest quiz scores dropped, and then you'll be retaking those. As far as labs, they do meet this week, so if you have a Thursday or Friday lab, you'll be going to that today or tomorrow. Otherwise, go on the first day. Your grade from lab is going to be 15% of your course grade, and I don't get that information from your lab instructor until the end of the semester, so you have to just keep track of that yourself. Most likely your lab instructor will have your running grade posted on Canvas. Okay, so that's the sort of administrative portion of today's discussion. Any questions so far? All right. So we're here to learn about electricity and magnetism. And we're going to start with what we call electrostatics, which is the behavior of charges when they're basically fixed in place. So we don't worry about motion yet. We just consider what happens when you have charged particles. How do they behave in the presence of other charged particles? And so as we go through, we're going to talk about charges. When we say a charge, we're really talking about a little particle that happens to have some electric charge, just like we talk about a mass in Physics 50 as being an object that has some mass. Okay, but a charge is just shorthand for a charged particle. And so let's try to get a little bit of what electric charge is. So I'm going to try a little demonstration. I have this device here called an electroscope. It's basically just a metallic rod right here with a needle that's carefully balanced. The needle itself is metal, and it's connected to this vertical rod by a metal axle. And this ring around it is just for structure. That is not connected to this rod with, it's connected with an insulator here, something that doesn't conduct electricity. And we're going to get more into that today. So the idea is that if we get something with static electricity on it, and that could be you if you're shuffling your feet across the floor. For this case, it's going to be a static charge that I put on this rubber rod by rubbing it on some fur. If I touch this metal, that charge gets transferred to the electroscope, and the charge tends to move through metal. Metal is what we call a conductor. It conducts charges. It allows them to flow. And so when I put the charges on the top here, they flowed throughout the metal, including this needle here that we now see tilted. And so the reason it's tilted is because like charges repel each other. So if we have, there's two types of charges, positive and negative, we'll call them. If you have two positive charges, they're going to experience a force opposing themselves. So they're going to push away from each other. Likewise, if you have two negative charges, they will repel each other. And so what we have is one type of charge, whether it's positive or negative doesn't really matter here, but one type of charge that flows across this metal, and it's spreading across the metal because it's trying to get away from the other charge, right? It's repelled by the other charge. So there's a bunch of charges. They're all repelling each other, so they spread out as far as they can. And the way that they can do that is when they get onto this needle, the needle gets pushed around because the charges on this needle are being repelled from the charges on that vertical post. And so the more charge I put on there, the further that's going to tilt the needle. Okay, so let's see what happens if I repeat this. We can see the charge is slowly leaking off the metal, and that's happening because there's humidity in the room. These experiments work much better in the winter when the humidity is lower, but we'll do it again. I'll put some more charge on, and I've literally recharged this. It's increasing the amount of deflection. Okay, what do you think happens if I touch that metal with my finger? Let's take away the charge. Let's see. Yup. The charge flowed away. It flowed onto me. So that's telling me that I am a conductor. Okay, so charge can flow onto me, and it actually flows through me into the earth. Okay, so the earth is this enormous conductor that can store a lot of charge. So we talk about something being grounded when there's a path that allows charges to flow into the ground. So if I touch this electroscope, we say it's grounded because the charge can flow through me into the earth. And the reason it does that is the charges are trying to get away from each other, right? They're repelling each other. And at first they were spread out on this vertical post and the needle, causing the needle to move. So that's good. That's as far apart as they can be when I'm not touching that. But once I touch that, they can flow through me into the earth and spread out, across the continents. It turns out there's really no easy way to measure this using an electroscope. But with this rod, I'm putting negative charge. I could put positive charge using different materials, like a glass rod and a silk rubbing thing would put positive charges onto that. So when we talk about positive and negative charges, what we have is atoms that make up objects, and those atoms have some structure to them where there's these subatomic particles in the nucleus that we call protons. Those protons have positive charge, and a neutral atom will have an equal number of small lightweight electrons that surround that nucleus. And it turns out that the charge on an electron is equal and opposite the charge on a proton. So a proton has positive charge, an electron has negative charge, but they're exactly the same amount. So if you have an equal number of protons and electrons in an atom, there will be no net charge. So when we talk about charge, if I put a charge onto this, really what we're putting on is some net charge, some excess of electrons, so that there's more electrons than there are protons in total on our object. So if you have an atom that has an extra electron around it, we call that a negative ion. So an ion is just an atom where the number of electrons don't match the number of protons, and as a result, it will have some net charge. So we can have negative ions that have an extra electron, or we can have a positive ion where one of the electrons has been ripped away. So it turns out that when current flows, current, electrical current, the thing that goes through these wires connecting all of our devices, it's just moving charges. We'll talk much more about that in a few weeks. But when electrical current flows, it's the electrons that are typically moving. So it's a little confusing because the direction of the flow of electrons means there's a bunch of negative charges moving. It's kind of nicer to think about positive charges moving, but that's not the way it works. Turns out it doesn't really matter. We can think about when I put a bunch of electrons onto this electroscope, we can think about negative charges flowing onto this, or we could think about positive charges flowing off of that, and it would have the same net effect. Okay, so we often think about positive charges as moving and talk about where do positive charges go, but typically it's the electrons, which are much smaller and more mobile, that actually do the moving. Okay, so there's these two kinds of electric charges, positive and negative. Protons are positively charged, electrons are negatively charged. There are other types of particles that are not really relevant for most everyday matter, but there are other particles that have charge as well. One thing that's really interesting is that the charge has some quantized unit. So there is a smallest amount of charge that something can have. And we call that the fundamental charge, E. So this lowercase e in Physics 51 is a symbol that you're going to use all the time. Just like you used lowercase g in Physics 50 for the acceleration due to gravity, lowercase e you're going to use pretty much all 16 weeks of the class. It's the fundamental unit of charge. The elemental unit of charge, I think, is what the E stands for. It does not stand for electron. In fact, the charge of an electron is negative, while E is defined to be a positive, or the absolute value of the fundamental unit of charge. So an electron has a charge of -1 E, and a proton has a charge of +1 E. And if you have an ion, it could have a net charge of -E or -2E or -3E, depending on how many extra electrons it can have, but it can't have 2.5 E or 1.4 E. It always has to be an integer number of that. Okay, so let's just test our understanding of this. When I rub this plastic rod on the fur, the fur becomes positively charged, the rod becomes negatively charged. So what I'd like you to do is talk to your neighbors, probably 4 to 5 in a group, and you're kind of spread out, so there may not be obvious groups. But see if you can make an argument for what happens to the mass of the rod when we rub the fur on it. Okay, the mass, not the charge, given this fact that the rod becomes negatively charged. Okay, there's 3 possible answers, right? What are the 3 possible answers? Yeah, so the rod gains, loses, or stays the same in terms of mass. Okay, any thoughts? Anybody have an argument for what it does? Okay, so in practice, the electrons are so light that even if we're moving electrons between 2 objects, it rarely affects their practical mass. So that is true, absolutely. But, in theory, they do have mass. And so if electrons are transferred, mass is transferred. So given that fact, what can we say about the mass of the rod after I've rubbed it? Okay, so if electrons are added to the rod, it would become heavier. So let's see. As I rub this, the plastic rod becomes negatively charged, so it's gaining electrons, right? So that makes sense to me, that it would slightly gain mass. Okay, yeah, so this is just a conceptual question. In practice, we never care about this. The mass of electrons is negligible. It's 1,000 times less than the mass of a proton, so it really has very little effect. If I were to take this rod and, let's see, I have some paper. I have a hole punches here, so just little pieces of paper, and hopefully you can see this. If I put this charged rod above the neutral pieces of paper, right, I did not charge those, but they're jumping up. They're attracted to the rod. Work with your groups to see if you can come up with an explanation for why something that's neutral, has no net charge, might be attracted to a charged rod. Okay, so this is a really tough one because we have these two seemingly straightforward yet contradictory facts. Opposite charges attract. Okay, that's something that maybe we can believe. The paper is neutral. It is not charged. I'm just telling you that. You don't know that, but I didn't rub it on anything or do anything to prepare it, so presumably it's neutral. That seems to contradict the fact that opposite charges attract. It would seem that uncharged objects shouldn't attract, yet we see that it can happen. Did anybody come up with a hypothesis, an idea that they want to share? Yeah, Jared? Okay, so maybe the rod is trying to get rid of its electrons, and maybe it's somehow transferring them to the paper. Is that okay? And charges do transfer through the air, particularly when it's humid, so they can flow through the air slowly. So that's a possibility. Any other thoughts? Yeah. Yeah, there are protons and electrons in the paper. Oh, maybe the charges in the paper are trying to move around. Okay, so that's an interesting idea. If the charge is moved around in the paper, let's explore that a little bit. So let's take my rod, and the rod was negatively charged, I think, right? And my paper is uncharged, so it can still have charge. It's just balanced. So if I draw 4 positive charges on this piece of paper, I can draw 4 negative charges, and that will result in a neutral little tab of paper. Okay, so if like charges repel each other and opposite charges attract, what's going to happen to the charges in the paper if they're able to move around in the paper? What's going to happen, let's say, to this negative charge right there? It's not working. All right, let's do it this way. Okay, so what's going to happen to that little negative charge if it can move around a little bit? It's going to move away. So let's say it does that. And that would be the case for all the negative charges, right? Oops, they're all going to get pushed away. And what would the positive charges do? They would attract, yep. Okay, so let's imagine that paper is really big. Then you could imagine that these positive charges here would be closer. Let's say there's some distance r1 away from the rod, and these negative charges are further away on average, some distance r2, can you imagine a scenario where that neutral piece of paper could now be attracted to the rod? Okay. So yeah, if this charge over here that's being attracted to the rod and this charge over here that's being repelled, if those are equal, there will be no motion of the paper. But the fact that the paper is moving means the attractive force must be greater than the repulsive force. And that might be because it's closer. Maybe this electrostatic attraction depends on the distance between the particles. If that were the case, then we would expect the action to be more significant when something's close by. Let's see if we can get a sense of whether or not that's the case. This exact thing that I described on the paper here is also going to happen on the electroscope. So before I touched the electroscope with the rod, let me just bring the rod close to the electroscope and let's see what happens. Let's see what happens when I bring it closer. The closer I get, the further the needle is moving. That seems to suggest that the closer the objects are, the stronger this electrical interaction is. Okay, and that's one of the key principles behind the electrostatic charge. It depends on the distance. Okay, so what we're seeing with the paper has a name. It's called an induced dipole. So a dipole means two ends in Latin. So di is two, pole is like ends. So this charge, this particle has two charged ends. There's a positive end and a negative end. It wasn't like that before we brought the rod close by. Before we brought the rod close, those charges were intermingled. But bringing the rod close by causes them to split apart, and we end up with like a two-ended charge. One end is positive, one's negative. That's called a dipole. And it's induced because it was produced by some external action, this rod. So we will see that you can have induced effects either in insulators, such as this paper, or in conductors, such as this metal rod. And we pretty much categorize materials into those two categories when we're talking about electrical conductivity: conductors and insulators. An example of a conductor is anything metal tends to be conductive. And it's due to the atomic structure of the metal, its location in the periodic table, that it has some electrons that are easily able to transfer from atom to atom. So they can flow from atom to atom. Think about this like you're at a dance and there's a really popular person who's just a social butterfly, and they can go from dancing with one person to someone else, and they can flow easily throughout the room. That's what a conductor is. An insulator is the opposite. The charges are tightly bound to the atoms that they're on. So think of this as a dance where everybody's dancing with the person who brought them. It's a bunch of married folks, right? They're not floating around dancing with other people. Okay, so anything that's metal is typically a conductor. There are other things. Water is a pretty good conductor. That's why people say, like, don't take your toaster with you into the bathtub. And you say, but I want toast after I get out of the bath. And they say, no, it would not be safe. What types of materials make good insulators? If metals make good conductors, do you have any sense of what make a good insulator? Okay, well, we made eye contact, so now you have to answer. Plastic is a good one. I'm sorry, what was your name? Natalia. Okay, Natalia says plastic. Why did you say plastic? Yeah. So you have some sense of this. When you have like a cable, right? The plastic jacket on the cable is not what carries the electricity, the current. It's actually there to prevent the current from flowing off the cable onto you when you touch it. So rubber, plastic, those are good insulators. If we look at this electroscope, I said that this metal conductor in the middle was not electrically connected to this metal ring that was for support. And you can actually see there's like a plastic sleeve that mechanically connects them, but doesn't allow the two metals to be in contact. Yeah, so plastics, rubbers. A simple rule of thumb is if you feel something and it feels cold, it's probably a good conductor. If you feel something and it doesn't feel cold, it's probably a good insulator. Okay, so if you touch metal, it usually feels cold. And the reason is things that are good electrical conductors tend to be good thermal conductors too. Typically your hand that you touch with is hotter than the ambient environment. So when I touch something metal, the heat from my hand flows across the metal and cools off my hand much more rapidly than if I touch something that's not a good conductor. So you can use that as sort of a guide until you get a better sense of what's a good conductor, what's a good insulator. So if we think about what happens when we induce a dipole or induce some effect in a material, so I'm taking my rubber rod, I'm charging it up, and I'm bringing it close to my insulator, inducing a dipole. What we have is these atoms where the charges are tightly bound to the particular atom they're on. So they can't really flow all the way to the other side of the piece of paper. What they can do is, well, in a conductor, they could just flow, just move all the way to the other side. In an insulator, they can just reorient themselves. So if we go back to that analogy of a dance, remember, a conductor is like going to a dance party where everybody's just friends and everyone's a social butterfly and they're just moving around. So now you say, okay, so we're going to let the men be one kind of charge and the women be another kind of charge, and there's equal numbers, so it's neutral. So somebody name something that women like that men are not interested in. Okay, name something that men like that women aren't particularly interested in. Nothing? It's okay. Just for the sake of argument. Okay, that's fine. We don't need to do gender stereotypes. I'm with you. Okay, but just imagine this. Imagine they say, okay, the men's room is over there and the women's room is over there, and everybody just had a toast of champagne, and now it's 30 minutes later and they have to pee. All right, so the men are going to go that way, the women are going to go that way. They separate. An insulator is like you have couples dancing, and let's say there's something over there that the men are generally interested in, and not so much the women, and vice versa over there. Well, they're dancing together, but the men are going to kind of maybe move so they can see that thing over there, and the women are maybe going to move so they can see the thing over there. And so you end up with all the couples dancing with the same, like, facing the same way. Like the men are all facing one way, the women are all facing the other way. If you can imagine that, that's sort of what happens in an insulator. The negative and positive charges move to different sides of the atom. So you have your protons here forming your nucleus. You have this cloud of electrons around it. And that cloud just kind of moves over to one side, just kind of check out what's going on over there. And as a result, there's a little bit more positive charge over there, a little bit more negative charge over there. They're not fully separated, but the net effect is that we have this charge distribution, this dipole induced. Okay, so in general, if I put charges onto something, if it's a conductor, they will flow all across the conductor because they try to spread out as far apart from each other as they can. If it's an insulator, they will stay where they are. If I have a spherical insulator, so a basketball is spherical and it's rubber, so it's an insulator. If I were to charge up this rod and I were to touch it to a basketball, I could transfer that charge to the area that I touch. But the rest of the basketball would not have any net charge on it because the charge can't flow. In a conductor, if this is a spherical metal ball, what in the world is spherical and metal? Yeah, I've got one right here. Something. We'll get to that in a minute. I don't know. There's not a lot of spherical metal things that I'm familiar with, but if we were to touch, the charge would flow onto it and then it would immediately spread out the way it did on the electroscope. Because in a conductor, charges can move. And if we have an excess of one type of charge, those charges will repel each other and try to spread out as far apart as they can. All right, so we've already done the electroscope demonstration where I touch the scope to transfer charge to it. Let me discharge it. We also did the demo where I bring the charged rod close to the electroscope and we still see an effect. We see that the needle moves, but when I pull back, it returns. What's going on there? Why does it do that? Any ideas? So this is a negatively charged rod. When I put it here, what happens to the electrons in the metal? Jared? They move as far away as possible, and that's down onto the needle. And so the needle becomes negatively charged, as well as this point down here. So when the needle and the vertical rod repel, we see that on the electroscope. So what does that mean about the top of the electroscope? So it starts neutral, so equal, negative, and positive. When I do this, we said that the negative charges get repelled away. So what's left behind? Positive charges. Bella? So that is a dipole when we have positive charge here and negative charge there. It's like a big dipole. What do you think will happen if I touch the electroscope, thereby grounding it, while I'm also holding a charged rod directly above it? Okay, let's go through this. First, the electrons are repelled. Now what happens to those electrons when I touch it? Okay. And now what happens when I step... Oh! Now it's charged. Okay, so the LAs have a little handout that they're going to pass out. I would like you to try to figure out what's happening. Draw little positive and negative charges, sort of like I did here. Here we go. Yeah, for each of these 5 different time points, draw where you think the positive and negative charges are. So initially, you should add some positive and negative charges just mixed about on the electroscope. Okay, so now what I'd like you to do is just put your pencils down. I don't want you to write this down, but we're going to go over it together. I don't want you recording it because I want you thinking about it. And then you'll get a chance to try it again. So when I bring the rod close by, we already described that the negative charges on the electroscope are repelled by the negatively charged rod. So they collect down here on the bottom, causing the needle to deflect, leaving an excess of positive charges up on the top, attracted to the negatively charged rod. We good with step 2? Make sense? Okay, so step 3. Now I touch the electroscope. In the diagram here, it's a wire connected to ground. Well, the electrons are being repelled from this rod, so they flow away through that wire into the ground where they can spread out far away from our rod. But our positive charges are left behind, so they're still there, still attracted to our rod. Make sense? Okay. So now I remove the grounding wire, or I stop touching the electroscope in the demo that I did. So all those electrons that float away, now they're trapped over here in the ground. Those are electrons that came from the electroscope, and they flowed off of it into the earth. And they can no longer come back because there's no longer a conducting path between ground and the electroscope. So now our electroscope is neutral over here because the negative charges that we had flowed off. And it's still got the positive charges up here being held in place, being attracted to the negatively charged rod. And so now when I take that rod away, those positive charges aren't just going to stay at the end because there's nothing holding them there. They're no longer being attracted to this rod, so they're going to just spread out. We have an excess of positive charges. So now they spread out all over. And that causes a deflection of the electroscope. So let me just repeat this again. Got my negatively charged rod. I'm pushing away all the electrons. I'm now allowing them to flow to the ground. I'm now trapping them on the ground. And I'm releasing the positive charges, which cause that needle to deflect a little bit. So one way to test if that really is positive charge, if I add some negative charge, it should neutralize. And I added too much. So it actually went down and came back up as I put more negative charge than I had positive. Okay. So now I would like you to talk to your neighbors, flip your paper over. You get to do your second try. You've just had it explained. See if you can explain it to each other and come to a consensus and fill out those that diagram again. Okay, so you can check your work up on the board. I put the solution back up. Bella had a good question, which is, I said that negative charges were the ones that did most of the moving. Electrons are mobile. They can jump from atom to atom. The protons generally don't. If you have metal, each particle of the metal is an atom. And while the electrons can move around, the atom itself stays wherever it is. So how is it that these positive charges were able to move down onto the electroscope in this last step? So do the protons evenly distribute when the electrons flow out? That's what the picture is showing. It's showing that they're distributing. And we can think about it as them moving, but in reality, they don't move. They're fixed in place because they're part of the metal, and the metal doesn't flow like a liquid. So whatever, if this atom at the top has a proton in it, that atom would have to actually move for the proton to move. And that's not what's happening. Okay, interesting idea. So maybe the protons aren't actually moving, but maybe like the electrons over here are being attracted to the protons, leaving behind an excess of positive charges. What do you think? Sound plausible? Yeah, I like that explanation. Okay, let's have more fun with moving charges. I have here what's called a Van der Graaf generator. How many people have seen this before? Science museum, YouTube video, something like that. Okay, so these things are famous for making people's hair stand on end. Anybody want to do that? Okay, so here's the deal. When I turn on the Van der Graaf generator, a motor will spin. This rubber conveyor belt will get charge placed on it by a high voltage supply here. That charge will move along the conveyor belt until it touches a brush on the top. And then that charge gets deposited on this brush, this metal brush that's connected to this big sphere. So where does that charge go? It wants to spread out. So that's why we have the sphere, give it a lot of space to go to. When Bella puts her hands on it, it's got another place it can go. Where's that? Onto Bella. Okay. Okay, so first thing I'm going to do, I'm going to take a piece of paper plate. Is this a conductor or an insulator? It's an insulator. I'm going to set it up on top. I'm going to take some packing peanuts. Do you think these are conductors or insulators? Those are insulators, yes, indeed. Okay. Whole bunch of them. All right, so what do you think is going to happen when I turn this on? Any thoughts? Colton thinks there's going to be a big explosion of packing peanuts. Okay, well, it's probably a bad idea to start with a null experiment. So maybe that's the case. Let's see what happens. All right. Did I lose my audio? Oh. Okay, so I guess I'm yelling. So what happened? The peanuts flew all over. Why did that happen? We're pumping charge onto this metal sphere, but the peanuts are connected. They're sitting on top of an insulator. Yeah, so we're inducing a dipole in the packing peanuts and the plate as well. And before we said the dipole was being attracted, but now it's the peanuts are being repelled from the plate. Let's see what else we can do. A stack of aluminum muffin pans. Go ahead and make a prediction as to what you think might happen here. Jared? Think they're going to fly off? Okay. So can you describe the motion of charges and the forces between them that might cause that to happen? Okay, so the charge that we put on this tries to get as far away as possible. Some of that's going to flow onto these conducting pans. And so I'm going to end up with this charged sphere and also a charged aluminum foil pan. I have 5, 6 pans there. Which one is going to get charged first? Okay, the bottom one. And then where do the charges go from there? They continue to move as far away as they can until they end up on the top one. Okay, so they're going to go to the top one. And then we have a top charged sphere, or top charged metal, and a charged metal here that are repelling. So let's see what happens. Okay, so they all flew off, one by one. Right? They didn't all fly off together, because the charges could keep moving further away from the sphere by going onto a higher and higher muffin pan until there was no higher muffin pan to go to, and then they just carried the pan off the top. It's going to change, or is anything going to change? If we do that. Maybe I should, let me do this. No, let me do this. Can charges flow onto the muffin pan anymore? No. So is anything going to happen? How many people think nothing's going to happen? How many people think something's going to happen? How many people think my microphone's going to miraculously start working again? Maybe. Let's see. That looks kind of like before. What's different this time? Yeah, yet the last pan never left. Why do you think that is? I'll tell you what, why don't you discuss with your groups? See if you can come up with a reason why that might not have happened. All right, let's go through it together. So when I first turned the Van de Graaff on, we're pumping charge up onto this metal sphere. It can't pass through the plate because the plate's an insulator. So why is it that I saw this first one fly off? Could it be something similar to what happened when I put the rod close to the electroscope? Maybe we were inducing a dipole, and maybe, let's say these are positive charges on here. I'm not sure if they're positive or negative. Let's say they're positive charges here. The positive charges were repelled. The negative charges were attracted. The top thing becomes positively charged. It repels from this and flies off. Sound good? Okay. We have a positively charged thing flying off. So we've taken away a little bit of positive charge from this neutral stack of muffin tins. Okay, so now the positive charges here are still repelling the positive charges, so they still move up until they're on the top tin, and then they fly away, leaving the remaining stack even more negatively charged. But all that negative charge gets pulled down, attracted to the positive charge of the Van de Graaff. So it's pulled down into the bottom tin, leaving behind a positively charged tin that flies off. And that keeps happening until there's one left. And then why does it stop?
Pulling together.
Yeah, so now we have a highly negatively charged final tin being attracted to this positively charged sphere. And before, the positive charges could flow up onto the next tin, but there is no next tin to flow to. So it gets a dipole moment. The positive charges move up and the negative charges move down, but they have nowhere to go, so they stay together. They still have a net negative charge. There's actually an attraction which holds it there. Okay, so let's just go over some of the terms we learned today and the key points. We introduced charge. Charge is a property of matter. We talk about charges, but they're really just little pieces of matter that have this positive or negative quantity on them. And if they have an equal amount of positive and negative charge, then they are neutral. So electrons are the negative charges. They're the subatomic particles responsible for the negative charge. And protons are the subatomic particles responsible for the positive charge. When you have an atom that's not neutral, it has extra electrons or not enough electrons, we call that an ion. And we categorize materials into two categories. Conductors allow charge to flow freely through them. Insulators do not. The charges may be able to reorient themselves and kind of look around, but they can't just go walking off. And we saw induction is the process of causing charges to move around from a distance using another charge. We did not get to Coulomb's law yet, so we'll cover that next time, and we'll end here.